Hey, how's it going? My name's Tony Perone, and I just want to show you a little bit about protein structure today. So here's your basic amino acid. You've got the uh, the alpha carbon here with the amino group and a carboxyl group, and our group hydrogen. The blue represents nitrogen, black is carbon, green is our group, red is oxygen, white's hydrogen. So the way a amino acid then connects to form a polypeptide chain is through a peptide bond, which is a condensation reaction. And the way that occurs is you have your peptide chain here, and you see an amino group here in the carboxyl. What happens is water is actually formed by taking the hydrogen. So there's the water, one hydrogen coming from the amino and one coming from the oxygen here. So that goes there, and then you form this peptide bond there, and that's what connects the chain. And the peptide bond has a planar structure, meaning there's not a rotation there due to a double bond character. But there is rotation within the polypeptide chain, and that's from the alpha carbon to the nitrogen, which is called the psi angle, and then the phi angle, and then between the carbon and the carbon, that's called a psi angle. And you can get rotation in the alpha helix from -60 to -60 for the phi and psi angles. So that's kind of what creates the rotation. And like I said, the peptide bond though has a planar, and you can kind of see throughout the chain, you got the planar, and then the way the alpha helix forms, which is the preferred secondary structure, is through that rotation of the angles. You can see right here you have the planar structure, which would be kind of the foundation for B sheets, which would be connected with hydrogen bonds, anti-parallel or parallel. And then to form the helix, what starts happening is you get the rotation, like I said, -60. And I know this will be a little bit imprecise here, but kind of show you the idea. Remember, the peptide bond does not rotate. Rotate there, and there, here, and there. And what starts happening is you start getting this kind of helix formation, and once again, the helix is stabilized by hydrogen bonds. Every 4 amino acids, you have these 2 hydrogen bonds that basically stabilize the helix. So kind of what inhibits a helix? Bottom line, alpha helix may be inhibited by large R groups, which cause steric clash, kind of the bulky R groups. Also, if you have hydrogen bonds competing with the R groups, or you have special amino acids like proline, which are rigid, or glycine, which are floppy, which don't allow for the structure to form. So like I said, secondary structures, you got the alpha helix, the B sheets, so I think of almost like strips of bacon, or you have a B turns, which you can find kind of that it basically turns back on itself, and that would be typically the special amino acids like proline or glycine form those. So now I kind of want to show you the hook here and a real-world example of a peptide chain, and this is a subset of the larger ferritin. And ferritin serves to store iron in tissues. And you can see here we have leucine, alanine, and glutamate. And the reason why I picked these is because these 3 amino acids tend to really favor an alpha helix because relatively they have small side chains that minimize the steric hindrance. And the Ramachandran plot shows that ferritin is mainly alpha helical, about 67%. And then the R groups, as mentioned before, have a major role in determining the secondary structure of the protein. You can see here we've got our bonds again. We have our amino group, and then the green represents that phi angle, which, remember, there's rotation around those, which creates that alpha helix character. And then you've got the psi angle between the carbons. The red represents the peptide bond, and then you see that throughout. And then you've got the amino acid terminus and the carboxyl terminus, and then the R groups are in the square, which you can see kind of in the boxes there that come off the alpha carbon. So again, this is a subset of the larger ferritin, which has many more amino acids, but there's your real-world example. And again, ferritin serves to store iron in tissues, so you can see biochemistry at work.